From DeepLite. We have Davis Sawyer, who is a Canadian tech entrepreneur and co-founder and CPO at DeepLite, which is a software startup founded in 2018 to make AI models work faster, smaller, and more energy efficient. DeepLite is based in Montreal, and Davis has been recognized as a C2 emerging entrepreneur and is a local chairperson for TinyML Foundation, which is a nonprofit and global ecosystem dedicated to ultra-low power machine learning. Prior to DeepLite, Davis developed statistical models for biopharmaceutical safety in Cambridge and built database software for oil and gas production in Houston, Texas. And Davis is from Texas, and hopefully we can host him here in person soon. And today we're really looking forward to your talk on how we can make AI models faster, smaller, and more energy efficient. Davis, the floor is yours.
Excellent. Well, thank you very much for that introduction. Thank you, Risha, and thank you everyone for being here today. My name is Davis. As mentioned, I'm one of the co-founders and leading the product at DeepLite, which is a software startup started in Montreal. And for the last few years, we have been at the intersection of some of the incredible advancements in what's called edge computing, neural network design, things like AutoML or automated machine learning, energy efficient inference computation. And so that's a space where, as some of you are probably very aware, is rapidly innovating and creating new and exciting breakthroughs, frankly, from things like AlexNet in 2012, about 10 years ago now, which was breakthrough in the ImageNet computer vision challenge, to now we have things like GPT-3 and just massive language models. So at the intersection of this space is not only how can we create exciting new possibilities, but particularly for us as a software startup, and particularly for myself, is how do we take these breakthroughs and apply them to real world problems across many domains, which we'll get into here. And so for this talk, we're going to get into some of the technical breakthroughs I just mentioned, and then in particular, which will hopefully be interesting, is how these breakthroughs can be used to solve real problems in terms of perception tasks for the safety of vehicles, for example, manufacturing inspection where a human operator can't expect it, but perhaps a small battery-powered sensor could. So there's this whole world of possibilities here. And as the title of the talk implies, we're trying to create new opportunities with a particular breakthrough called ultra-low bit precision neural networks. So very excited to be here. Thank you again, everyone, and let's dive in. So very quick background on the company. So we are a small team based here in Canada with some international research partners. We're just over 30 people. Myself, one of the co-founders. I met our CTO, Asan, who did his PhD in high performance computing in Montreal, was previously at Morgan Stanley, SAP, Microsoft before that, and also our CEO, Nick, who's based in Toronto, is a serial entrepreneur. And the three of us really got along on the idea that, while deep learning is exciting and there's all these, amazing things happening we just mentioned, the big question is how do we make it more accessible and affordable? And while the economics of it might not be something that is inherently, baked into research, that's where solving these cost-effective problems, like is mentioned here, faster, smaller, more energy efficient, that's where we can see, the creativity of the community flourish and come up with all sorts of new kind of cool products, which we'll mention here in a second. Really, with the backbone being some of these fundamental advancements in the research community. And so, yeah, we're very proud to be a sponsor of the TinyML Foundation. For those who haven't heard of TinyML before, it is a rapidly growing community around ultra-low power machine learning. This includes things like hardware design, algorithm design, new software tool chains. It's a whole brave new world out there. So I'd highly encourage you to check that out. And yeah, just list at the bottom there, those are some of our partners and investors, which we're very, very grateful for. And we do collaborate with some well-known academic institutions such as Mila under Yoshua Bengio here in Montreal. So to give a little more context to about what we're going to talk about with the application of these low-bit precision neural networks are really the tasks around how to do fast computer vision on low power devices. And the combination of those two things is quite important. Fast, when we talk about fast, we're talking about the inference. We're talking about the detection. Once something's deployed out there, maybe you can train it quickly, you have a huge supercomputer, but at the end of the day, you need these fast, real-time predictions for a lot of these things. A great saying I once heard a few years ago is, training is once, but inference is forever. And so when we talk about fast computer vision, we're talking about fast inference. And low power devices, that's the cool part we're going to get into a bit more in that these low power devices are everywhere. They're in our hands, they're in our cars, they're on our heads. There's just billions and billions of connected low power devices that can benefit from these types of applications. And just this video on the right here, what we're talking about are things like tasks that have been researched heavily, but are now at a stage where products are being built around them because of some of these combinations of interdisciplinary application to have very robust, very accurate, and of course efficient AI in the real world. So to anchor all of this and to anchor what we're really talking about here, as the talk title implied, there are endless opportunities. And while cloud has been a big trend for the last decade, it's become a major trillion-dollar computing paradigm. And some of the talks earlier in this series have really focused on, oh my goodness, how to create the world's largest chip, for example, and in all sorts of incredible ways to train and build highly complex models. And inference is very common in the cloud as well on different types of processors. We fundamentally believe, because of these properties here, really a flywheel, really, that edge AI can be and will be bigger than the cloud. And there's really 4 components here that we like to highlight: just the sheer number of devices, the fact that these devices are connected. This statistic in the bottom right here, about 50% of data analysis will be at the point of capture by 2025. That comes from Gartner, because the premise is really that, it's not practical to be constantly offloading things to the cloud. It's not cost effective to do so. But the challenge being is, for a developer, for people trying to research and produce neural networks that can be deployed on the edge, it's a non-trivial task. And so with this pursuit of deploying on the edge, once AI becomes untethered, decentralized, and everywhere, that we believe fundamentally will be the holy grail here. And I want to make one quick comment that it's not one versus the other. Edge and cloud often are hyped up a lot in media, but when you look at the technological level, they're actually very interconnected, and there's multiple tiers to this that I think are being unlocked and understood as we speak, from telecommunications to also the AI side of things. And so as many of us are probably familiar with, but just to really drive the point home, the challenge as well, deep learning at the edge is exciting. It's tremendously difficult because these neural networks have become so big and so slow when we talk about edge inference. The high computational complexity, millions, if not billions, of expensive floating point operations for each input, and these inputs can be continuous. We're not just talking about taking batches of images and analyzing them offline. We have a live stream of video. We have a live stream of user submitted content that needs to be analyzed. The middle one, which is a really big one that we're going to talk about in more technical detail in this talk, is the memory footprint. So once you have a trained neural network and you want to load it onto a device, you now need to consider not just maybe your own application, but this is a device that's running multiple applications. You have to now consider CPU usage. How much on-chip memory do you have? And these are things that are kind of in constant combat between what a device is currently doing and adding new capacity to it. There's this endless capacity to consume capacity. And while there's been breakthroughs in cheaper memory, new types of memory, the pace of neural network innovation vastly exceeds that. And then the third one here, which we talk about TinyML, and I think this car example is kind of good for this as well. Even if you have a neural network deployed on the edge, and say it's fitting your on-chip memory, say you've got the computational cost down to just maybe a few 100,000 Mac or something, now you consider the power consumption. Edge devices can be connected, but often it's really about battery life. That's the flip side here. Is even if a gas vehicle is off and you want to run some application on it, which is actually something we'll talk about later, you need to be mindful of power. The real world has resource budgets, and I think that's really the kind of takeaway from this slide is, okay, neural networks are exciting, but when we deal with the resource constraints, computation constraints, how do we fit our AI into these constraints? Doubtless there's new hardware coming, doubtless there's incredible innovations happening there. We want to make a world more fit for AI, but at the same time, from a software perspective especially, it's how we make AI fit into the world. And that's kind of the premise of this slide. It's a famous chart. I think it's been around for maybe a few years now, but it's super, I think, telling, and has only kind of ramped up even since this chart was produced. I think even the authors of this, had some inkling that this steeper slope is just getting steeper, and that's because of, I think, an obsession, but also a strong academic and industrial pursuit of what more can we do with more complexity, and we're still just discovering that. But coming back to the point about tying this innovation to the real world, as we have, models like just massive transformers now, we even have, vision transformers, which are using the attention mechanisms of convolutions. Training complexity has unlocked massive potential, but coming back to this lower sloping graph, Moore's law, really, no networks have hardware has limits, but no networks don't. And really, what we're talking about is denser scaling here. That's I think one of the things that kind of can get lost sometimes in this is really that's one of the challenges here. So although there's ASICs, there's dedicated hardware that are really addressing this from both training and the inference side, the synergy of the two, the synergy of kind of bringing these two together for various applications, be it NLP, be it computer vision, that's where, coming into the technical content of this talk, that's the intersection that we're most passionate about at DeepLite, and very fortunate to intersect with hardware design companies, IP vendors, the algorithm community, open source frameworks, for example. And really, that's, I think, what a lot of forces are vying for in the ecosystem, is to bring those two together. That chart's going to keep going up, but there's still endless possibilities to merge the two together. So taking this back to edge, back to what we're going to focus on in this talk about low bit precision neural networks and neural network compression, the idea here is that we have to bring the inference computation to the very edge, as close to the edge of computing as possible, because you talk about inference time when you load in an image or load in some input you want to run inference on. As you cascade down this hierarchy, obviously you have more capacity, and neural networks need that capacity, but you're going to lose a lot on speed, which of course going off chip is going to have a lot of power costs as well. It's going to kill your latency, and that's the challenge we're talking about here. Is okay, we want to bring neural network computation here to this edge of computing to increase our speed while saving on the capacity. Size is the big challenge here, not just size in terms of maybe how many parameters your network has, but actually the size at runtime, at inference time, where you now have to store your activations, you have to process that input, and you want to do it as fast, as cheaply as possible. And so what this green text is referring to is, okay, and I guess the one clarifier is not just model size I just mentioned, it's really the footprint, the memory footprint, as the previous two slides indicated. We want to optimize these DNNs to save on this model size. The big thing here is while maintaining accuracy. And so the way we look at it is this concept of, okay, we have these constraints, be it the amount of on-chip memory you have, your acceptable accuracy for your given task, you have your data set, you have your model that you've trained. How do we input these things, these constraints, data, model, into a system, and then ask the system to optimize this neural network in an automated way? Because when you think about the way to approach this, there's many different ways, and there's tons of stuff proposed in literature. But when you think of this is, okay, it's really a design space exploration problem. And as we get into this in the next couple of slides, it's okay, how do we explore this design space of different sizes and different accuracies in a way that makes human audit or human guided search much more efficient and friendly? A lot of best practices nowadays are kind of to just, okay, go take the highest performing detector, go take the best performing classifier, whatever your task is, train it on your data set, and then deploy it. And this is a common behavior that's really accelerated the deployment. It's fantastic, the efficiency and ease which you can kind of just go pull something from a GitHub repo or Model Zoo, train it and deploy it and start playing with it. But coming back to the point about real world deployments, these aren't toy problems where, the difference between 90 and 95% accuracy is a go or no go. The difference between 100 millisecond latency or 500 millisecond latency is a go or no go. And that's where we've oriented a lot of our efforts, a lot of the research we're going to present here on that exact problem. That exact problem of how do we enable the developers of the world, the neural network developers of the world, be it in academia, be it in industry, with the right tools, the right, not just optimization algorithms, but actual optimization software that can help them train better networks, deploy better networks, and iterate over this cycle as much as possible, as much as necessary. So this is, I think, the technical premise for what we're going to get into here today. And so, as I was just referring to, this is the pipeline that we've built at DeepLite, and within this kind of middle box here, we've packed a ton of cool technology, a ton of research from our partners and internally to make this possible at the technical level. Things like I'm sure some of this terminology may be familiar: channel pruning, filter pruning, neural architecture search, which is a big topic for the last few years. Even older techniques like tensor decomposition. The kind of rule here has been there's no silver bullet when it comes to solving this problem, because data is different, data distributions are different, device deployments are different, and even if you're deploying the same object detection on the same CPU, there may be different constraints you need to factor in that will guide this search and make this possible or not possible. Whether you're talking about a place with limited internet infrastructure where you need to do some kind of medical imaging or diagnostic from a mobile or tablet, or we're talking about a sensor in a rainforest that's looking for moisture to see if there's some risk to the life in the area. The real world has these constraints. We have the algorithms and tools to address these problems we just mentioned, but what this pipeline or what this figure is trying to tie together is from both a software development perspective, from a model design perspective, and then from a deployment perspective, how can we tie it all together to address the problem, whatever that problem may be. And as the title indicates, this is maybe more of a industrial leaning problem, but even, of course, in research times, sometimes data can be very sensitive. It's not just about security or privacy. It's really about the sensitivity of it, and also the bias of it. I mean, that's not something we explicitly address, but it is remarkably important. And so yeah, that's the state of development here in terms of addressing the problem we just spoke about. And so now we're going to kind of dive into more of the actual techniques that are being applied, that are being used to bring this together. And yes, that's really kind of the tagline here, is accelerating this design and deployment. So as I mentioned, that middle box has some interesting technology in it. So let's go into what's been previously done. The low bit precision stuff is really the focus for today. But to preface that, we've looked extensively at, for example, before we start to quantize things and start to play with some of the lower level optimizations, which have consequence at the hardware level, what we started initially was, okay, these architectures are often trained on things like ImageNet databases or COCO datasets, or these off-the-shelf datasets that are great reference and great initial points to then transfer learn on, say, a proprietary dataset. But the bottom line is that they're over-parameterized and under-optimized for the distribution of someone's actual dataset. While they're great starting points, it's not intuitive to say that this is the right model for the right application. And so the way we've looked at it is, okay, well, let's explore the design space. You have different convolution layers with different filter sizes, with different number of filters, with different connections, different activation functions, different layer types, different, all sorts of different stride, all these different things. So that's a multi-objective optimization problem that maybe a human being is not explicitly suited to solve. We have great abilities to at the training side to get a good nature of the problem. What are some of the challenges, whether it's the orientation of a camera for a given task, or maybe if it's NLP, you have some intuition about it. But we start to talk about, okay, let's explore all the different trade-offs of this neural network design. That's a good design space exploration problem. Granted that you can meet these constraints. And so the way we've approached this has two sides to it. When we put in some neural network, put in some data set, and put in some constraints like acceptable accuracy into the software stack we just showed before, what are the sensitivities in a model that we can exploit? So kind of like a more of a sensitivity analysis of the different layers and different aspects of a model, which is also important for the quantization side. And then once we can learn or understand the sensitivities related to some output and input, what can we do? What are the actual modifications, kind of like surgery here? Okay, what are kind of the things we can snip and cut and reconfigure to better serve the tasks that we want to do? And so this is a very classical architecture, the VGG classifier, just for illustration's sake. So, but a pretty standard topology, when you look at classification backbones with just new iterations on them, like with mobile nets and efficient nets and using depth-wise convolution, et cetera. The task now is, okay, learn the sensitivities and then make some transformations to the network that better increase performance based on the human guided inputs. So how this looks and what we've dubbed this concept as, which actually works quite well and has some kind of interesting, it works very well. It has some interesting informational aspects behind it as well. But the concept we've taken that we've worked on before and published in AAAI and I've showed Tiny Mail before is this concept of networks within networks. Given some classifier architecture like you see here, what we found is we can actually approximate a part of the network with a smaller and thinner neural network. When we come back to the task of how do we bring this model as close as possible to the edge of computing, where size is the biggest challenge, what we've done is say taken an approach where we can find the sensitive layer. Let's just say arbitrarily this is a sensitive layer here, and on its current size it's 2.3 megabytes. We can approximate this big convolution with a series of thinner and deeper convolutions, which has a massive reduction in the size of the model. So not only can we save on parameter count, can we save on the on disk size of the model, but actually at inference time, this also saves us on the memory footprint as well. And the interesting thing is that this isn't heuristic based. This isn't like, well, the middle layers are less sensitive than the initial layers, or the later layers less sensitive than those layers. This is actually something learned by some of the algorithms we developed, where we input, again, constraints, model, data set, and then learn this kind of layer selection and layer transformation type. That's some of the technology we've been providing for some time in the market. At the end, we'll talk about the DeepLite neutrino stuff that we're using for also the quantization side of things as well. And this is really coming back to some of the big trends here. This is really an AutoML task. Maybe that's a familiar term, maybe it's not. AutoML meaning the process I just showed is something that's kind of done, really type in one line of code. I want this model, this data set. This is my acceptable accuracy. Press run. This is where this agent kind of goes through and starts to learn these layers. It's actually a rapidly fast process. We don't want to introduce retraining. It's something super important here, or too much retraining, because that's going to kill the whole iteration cycle here. And as you can imagine, in a literally endless design space, this is an NP hard problem. You can't brute force it, and you can't explore all possible designs. So what's been kind of really cool here is using new advancements. So when we're doing this layer selection, using things like attention mechanisms to actually try and do this sensitivity analysis has been very fruitful. Really, that's something that we continually compound on. In terms of retraining, maybe instead of fine tuning, you want to use something like knowledge distillation. Knowledge distillation is something Hinton proposed in 2015. That's something where when you apply it to this type of problem, compression architecture search has huge dividends. There's a few complexities there, such as whether you have a softmax output or some other type of output that you'd want to use to guide that distillation or to assist that distillation, because we're trying to get basically information about the last layers of the network to use to train another neural network. That's the whole root of distillation. But the bottom line is that, coming back to the over-parameterized, under-optimized concept, this is a really great way of exploiting those inefficiencies in a neural network after training. This is a post-training task, and getting huge savings on our model size. So the previous work, as I mentioned, on this network design space exploration is where we found ways to really compress these networks. And that's why this is framed as an exploration problem. So you look at the steps here, just to wrap up this whole architecture search or design space problem that prefaces the low bit precision stuff. You want to select some layers. The complexity would be really based on the number of layers in the network, which actually has very interesting implications. We talk about our experimental results. Deeper networks obviously have more layers, which can either be a good thing or a bad thing. Often sometimes people wonder if the complexity comes from the model. What we found consistently is that the complexity in terms of optimization comes from the data. It comes from the complexity of the data. How many classes do you have? How well are these classes represented in your data set? And the model exploration task is really trying to, of course, maximize the mutual information between what you're getting from your model and what's there in your inputs and outputs. So yeah, the layer selection problem here. But then we want to do some transformations to it. A super key thing here, we talk about preserving the network shape in one way or another, is that you want to preserve the input-output shape of those layers we change. That makes this problem a little bit hard, because if you start to play with the input-output shape now, it has a cascading effect on the whole network now. And from a software design perspective, becomes pretty complex to manage all these different changes you're making. So one of the things here we're doing is we are basically preserving input-output shape, approximating with different layers, and then we use this new series of layers and this distillation I mentioned to get the accuracy back up. So it's like, hey, I think this layer is sensitive. Let's change it. Is the accuracy acceptable? If yes, keep compressing, because we want to maximize the compression rate while maximizing the accuracy retention. And that's a variable. Actually, we talk about this problem in the software we use. That's something that the user actually specifies as an explicit value. They'll be like, hey, my network can be 90% accurate. It's currently 98.5. You get a 0.5% delta to try and compress it more. Of course, the bigger the delta, the more compression you can get, and vice versa. But again, it's an nonlinear problem. It's not something that we can say explicitly higher delta always means higher compression. That's why this is kind of a tricky exploration problem, is that you can find local minima, and then you can find some very rigorous design space exploration. So that's the previous work here. Quickly, just to testify to how useful this can be. And again, this is done pre-quantization. All this compression is done with 32-bit weights and activations. And even then, even on data sets that are very complex, Resonant 50 is still actually a very common backbone in terms of benchmarking and things like this. But it's vastly, still over parameterized, even talking about ImageNet, if you have efficient design space exploration. And the thing is, when you talk about real world problems and real world data sets, that's not always represented well by these open source data sets you see here. Same thing for Coco, which is just a bigger, more multi-classes than VOC, for example. And this is super exciting because what it means is that these networks can be iterated on, improved on beyond just the advancements in architectures, which can often have implications at hardware level as well, meaning things like depth-wise convolutions or different more efficient activations and things like this. So that's the previous work we've done going back a few years. We've published on this in AAAI and a couple other places, as I mentioned. And this is all done pre-quantization, as I mentioned. The one last point about this, and the same applies to even the most latest models like ULV5 version 6 and all the latest stuff out there, efficient nets, etc. One of the premises that we've been fortunate to work with industry on and really actually, I would say, help educate and work together on by getting feedback from them is that it's train large, then compress has kind of been our motto for a little while here, when allowed, because say you want to just start from a very common behavior. I'll take a step back. A very common behavior is to take the most compact detector if you want to go to the edge, train this compact detector, like MobileNet V2 SSD Lite is a very compact detector, just about 13 megabytes, very fast on like mobile phones, for example. But you train a lot on accuracy. I mean, YOLO V5 is already in the high 80s, I think 90s. Either YOLO V5X is huge and has a very high performance. It works very well on real world problems. YOLO V5 Nano is much smaller, more towards like the MobileNet V2 side. But when you talk about the way that you can approach training for these models, the most consistent best practice that we've seen is actually to train large and then compress, as opposed to just taking whatever compact detector you have, because you'll lose, it's like a sponge, you'll lose information with this compact detector training. If it's acceptable for your task, then by all means, right? That there's no reason not to use what works. When we talk about more complex problems, we're talking about 98%, 99%, 99.5, 99.999. Some of our manufacturing quality inspection tasks are like that. Medical is obviously very like that as well, depending on the task. That's where this practice starts to pay big dividends, because we're exploiting the high parameterization of the initial model to then have a better search to converge on a more compact model that might be better suited for the task than just taking whatever, state-of-the-art detector, state-of-the-art classifier, whatever it is, segmentation model, same thing, off the shelf, just because that's what's there. I think that's the main takeaway from this design space exploration stuff is really this here. So with this said, we can make models more efficient, and it's been well known for some time now that even going back to like LeCun's early work on pruning and sparsity is another big topic here. Sparsity, not just in terms of weights, but also sparsity in terms of activations. There's a mass amount of stuff to exploit just at the node network design level. However, in recent years, there's been a lot of interest in let's exploit at the bit width level of the weights and activations these informational efficiencies as well. And as was mentioned on the previous slide about int8 quantization, integer 8 quantization has become a best practice on the edge devices for some time now. 4x on the floating point 32 model has energy savings as well, can be very fast when implemented on certain hardware, like ARM CPU, for example, and other types of hardware. But the thing there is that we can go lower. And that's where I think at DeepLite we've been pursuing for some time now in collaboration with also Yashua Benjo's lab at Mila was, okay, we can do this great neural network design stuff. Now let's start to really explore in parallel the quantization stuff. And that's where this whole transition here. So this is the future. Actually, the future is now in the sense in that we actually first unveiled our work on binary and 2-bit networks at the PyTorch Developer Day. I mentioned TensorFlow and int8 quantization has been the de facto for some time now. Maybe some of you have played around with quantization, both training aware, but also post-training quantization for some time using TensorFlow framework, and others have this capability as well. But in particular, we've been working in the PyTorch framework, but this is true of basically every framework out there right now, is there's no way to run these ultra low bit networks, despite, as this chart on the right shows, the clear energy savings. And so the way we looked at this is, as was mentioned before with the edge of computing slide, most of the inference performance is lost. The memory transfer, this offshoot memory access drastically increases the power consumption, depending on your type of memory and latency. of course, we have hardware where we want to do in-memory computation or flash or analog or memristors and all this kind of super cool stuff. And that at the end of the talk is where I might get really excited to start to talk about that too. But that's where this really starts to intersect. So many of the quantization techniques, like in Tate, have been shown to be very robust accuracy depending on your task. FP16 in GPUs is very commonly used, just bfloat as well. But why this has been such a challenge, as you can suspect from just the informational aspects of things, is that when you start to go to very low bit weights activations, consistently, especially for a lot of challenging tasks in vision and also other domains as well, be it speech to text, etc., they lose too much accuracy. And so where we sought to pursue this first and foremost was, okay, that's the first challenge. That's why no networks have been adopted was, they just blew accuracy out of the water on various tasks. Why low bit precision networks could be fantastically exciting is if they're accurate, they're also, and again, as this chart shows, they're super, super energy efficient. And so being in the space like TinyML, being in edge devices, that's something that we've been heavily pursuing and are very excited to share some of the results and some of the techniques that we've exploited here. This mentions integer 2 and integer 4. Actually, we've more looked at 2-bit and 1-bit networks. And I'll talk about how we do this in just a second here. But the main premise has been, okay, we post-training quantization using some scaling factor and trying to quantize your post-training can be nice because you don't have to retrain the model, but that loss of retraining or that loss of information is why we're losing too much accuracy. So let's revisit that. And quantization or training has been a super big trend the last couple of years from various places as well. Is okay, let's now try to not just quantize to a specific precision, but let's quantize to an arbitrary precision that is the best configuration based on the user's constraints. Looking at how we address the architecture search problem of, okay, data set, model, constraints being input, the same premise applies here. We want to input some data set, some initial model, some constraints like accuracy or latency, for example, and then learn the optimal precision configuration based on what that use case is. And as last bullet point indicates here, actually implementing these low bit precision operations or ultra low bit, meaning sub 4 bit in hardware, that's the future here. So looking at our approach, and as I mentioned a bit just previously, current public domain AI runtimes, there are some specialized frameworks from hardware vendors, but even then it's a very early field. They only support up to 8-bit. And while 8-bit has paid dividends for the last few years in terms of more efficient mobile inference and running on devices like Android and others, we wanted to look at how to exploit the ultra low bit precision. So I'll just walk through this. It's a fairly generic equation for quantization. Being in industry, I guess I can't share all the secret stuff, but I did leave my email if you want to join and pursue this question. I'm more than happy to talk about it more. But at training, so we want to quantize an input tensor as shown here, and really it's all about this scaling factor where we want to maximize the accuracy retention, of course, based on the user's defined accuracy, and basically we have the ability to learn 2-bit and 1-bit weights and activations. That's super important here because just quantizing weights, if your activation is still in full precision, you're gonna have nearly the same bottleneck as before. So the trick is both quantizing weights and activations, which means you have much less information when you talk about 2 bits versus a full FP32 multiply accumulate operation. So that's the trick here. Is okay. Let's try and learn. Let's have an algorithmic way of learning the scaling factors so that our quantization error is a minimum, and we get real 2-bit weights and activations. When I say real, this is where the runtime aspect becomes important, is because we don't want to just implement these low bit models on FPGA, for example, and simulate the performance and get some energy metrics. We actually want a way to infer these 2-bit models. And so you talk about PyTorch framework, for example, there's no way to store this 2-bit model you might have created. So let's say you have an accurate 2-bit model, which we've done. Now you want to run this model. And that's the flip side of this, where we leverage these low-level hardware intrinsics. Specifically, at this point, we're leveraging the Neon instruction set, such as ARM Cortex-A CPU. That's been the first place we've actually really applied this 2-bit network computation, 2 and 1-bit network computation to a real hardware. So coming out of the lab, we saw this great accuracy performance. I'll share one example in a second, but to give a reference, say for a ResNet model, 2-bit models are maybe less than a few percent, like 4% less accurate than a full precision model in top one accuracy. So that was like crazy to us, is that we could have such an accurate 2-bit, 1-bit model. Then we actually wanted to run this 2-bit model on real hardware. That was where things started to get really exciting. So as you see here, this is one of those benchmarks I just referred to. And the CPU we're using is the one in the Raspberry Pi 3B Plus and Pi 4B. This is in the first case, it's a quad-core ARM Cortex A53 CPU. That's the lower-end Pi 3. And in the Raspberry Pi 4, it's a quad-core ARM Cortex A72 CPU. So these are still, you know, in the milliwatt power budgets. They're like kind of little computers. I'm sure everyone knows Raspberry Pi and these kinds of things. Why we did this, I'll get to in a second, is because these are the same CPUs that are applied in like automotive grade CPUs and security cameras and just a whole host of devices that are using a very similar performance grade CPU, but haven't adopted deep learning because it's been too slow. And so with this premise here of accurate low-bit models, meaning looking at Onyx models, so Onyx is a common runtime. Say if you want to train in PyTorch, Onyx RT has great compatibility to run this model on various devices. So Onyx runtime, 93% accurate for VWW's visual wake words. It's a simple classification task, person, not person. That could be any two classes, but in VWW data set, it's person or not person. So you can imagine this lends itself to like an Alexa device or like home security cameras, things like this, smart doorbells. Basically, we found that on a Pi 3B Plus, latency was like 600 milliseconds. And on the 4B, so the A72 cores, it's about 300 milliseconds. Because of motion, because of robustness to movement and things like this, that's why these devices weren't able to adopt it, because you're talking about 2, maybe 3 FPS. And if it's a home security camera, someone can be in and out of the field of view well within the, you know, that time frame, depending on, and then you don't get enough information about them. So we ran these 2-bit neural networks and 1-bit neural networks. That's what this is saying here, is 2-bit activations, 2-bit weights, 1-bit activation, 2-bit weights. If it's still almost as accurate, this is a toy data set. Like VWW is not representative of an actual production grade person detection data set. But for the sake of demonstration, you know, the model is now getting to like almost 20 FPS on a CPU, low power CPU. So that prompted a lot more development into, okay, if these ultra low bit models are accurate and they're running a lot faster than like an 8-bit model, what else can we do with this? And so we then applied the same quantization to the YOLO v5 family models. So like earlier we were talking about VGG and previously just ResNet. So these are obviously older, but still relevant architectures. The YOLO v5 is one of the highest performing models out there. There's now v6 that maybe has been worked on. Maybe there's a v7 now, but v6 was released earlier this year, maybe late last year. So we took this YOLO v5 v6 from the Ultralytics repo. If anyone wants to play around with computer vision, just a quick side note, Ultralytics has a lot of awesome models to start kind of get up and running and just build things with. So we then took this 2-bit model, 2-bit model in this case, and built an inference engine or runtime. That's what RT stands for here. So DeepLite RT is this DeepLite runtime that leverages the neon intrinsics in the ARM Cortex-A CPU to do the convolution operations far faster than if you wanted to do full precision model. We pack these 2 models in a way that can be compiled in a way that's very well tuned for these hardware. And we said, okay, how is this going to perform here versus like something like int8 at a TF-Lite using XNNPACK. XNNPACK is a great library to really boost your performance. TensorFlow Lite is maybe a bit better than TensorFlow, but TF-Lite plus XNNPACK is super fast on CPU. And so we then applied this 2-bit model and compared them with YOLO v5. YOLO v5S is small here, YOLO v5 small, YOLO v5M is YOLO v5 medium. And what we found is that not only are these 2-bit models just as accurate as we saw, almost just as accurate from the previous slide, but they're much faster. And 1-bit is even faster. And so what this has meant, when we talk about people in the PyTorch community, for example, is you can go from like maybe 3 to almost 10 frames a second, or in this case, 1 frame a second to 3 frames a second, which actually starts to make a meaningful impact when you're trying to deploy object detection retroactively to a CPU. And one of the undertones of this has been, I'm sure many people in this space are very aware of the semiconductor shortage and the challenge of manufacturing a new fabrication these days. So a lot of companies in the industry have looked to add AI to their existing devices. This has been a trend already for a couple of years, few years, but it's really accelerated under this circumstance. we can add new AI features to existing devices without upgrading the hardware, but only if and only if they are performant enough to get there. We can't expect NPU or GPU, embedded GPU performance of these devices, but excuse me, we can almost get there. And that's what's been so great about this 2-bit and 1-bit stuff, and ultra low bit precision quantization has been achieving this latency. So kind of to summarize what we've seen, we're talking about a 16x size reduction on top of the previous work. So if you've compressed the model 3x, and then quantized it down to 2 bits, you're getting a 48x, or sorry, the 2xp, the 32 in this case. So that's super exciting and super helpful. Again, we've exclusively focused on Cortex-A CPUs at this point, which is getting nice speed up. There's a lot of devices now that use ARM-based CPUs, ones that weren't using it before, such as the likes of Apple, now building around ARM as well. There's even ARM-based CPUs, like AWS's Graviton in the data center that we've worked on. So these are like multi-core ARM CPUs based on Neoverse architecture. So that's what we've done here. And the last bullet here is important because we talk about the power cost as well. Going back to the previous slide with the numbers for the Google TPU, when you start to remove these expensive operations, you have not only room for more neural networks on your device, so that freeing up capacity to do more has been a very, very powerful trend, but also just the power budget. Battery life is again one of those go or no go things for industry often, and so we've been really fortunate to apply this technology to a way that can help address that. One of the last points here I alluded to a little bit previously, but has been really well received by the likes of NVIDIA and ARM, even though they're not merging, as people probably know, but this has been, they're obviously still very prevalent in the marketplace. What we found, we didn't expect this, what we found was that these 2-bit models are like almost approaching GPU level speed from the CPU. And so to break down this chart on the left for you, shorter is better here. What it is saying is that TensorRT, which is an optimized library for GPU, this is a Jetson Nano here. It has a quad-core ARM Cortex-A57 on it. So on this platform, the GPU can run the model at basically 2 times the speed of DLRT, which is our inference. DLRT itself is like maybe 3 to 4 times faster than these frameworks on top of it. TVM, which is an interesting thing, we can probably talk about this, some questions around TVM in this space. TVM is a compiler, open source compiler, used in Washington. It's also some stuff built around it commercially. TVM is very fast. DLRT outperforms it, almost approaching GPU level speed. So what this has led to is the thinking that, well, the ARM CPU is kind of like this, it's this thing that handles the dumb stuff. It doesn't get to handle the AI processing because it's just this little ARM CPU, let it just control and do some basic logic functions on it. But what if you could offload some AI to the ARM CPU, some little wake up stuff, classifier or something, and then do the heavy duty AI on the GPU? Because the GPU is overkill for a lot of AI tasks, to be frank. And so the idea is that we can actually get more out of the same platform by offloading some AI to the CPU and then doing heavy stuff on the GPU. A good example of this would be large-scale object detection for the security of an airport, for example, where you have many classes and running object detection constantly is impractical. But if you could have a classifier wake up for certain things like a threat or a person or something like this, and then do detection, it has a big impact on performance. Another good example is super resolution. So do some kind of detection or simple stuff on the CPU, and then run the heavy upsampling or whatever it is on the GPU. That's the kind of stuff we're starting to see wake up and come out of this breakthrough low bit precision work. Putting it all together, so just a few minutes here left to kind of go into detail on a couple of I talked about creating new opportunities, so I want to talk about some of the new opportunities that are being created here. Some from a software development platform, when you put together this compact model design, this DeepLite Piccolo thing is like, we have compact networks as well. So not just like MobileNet SSD and things like this, but some of our own custom created detectors. The hardware agnostic optimizer, that's what really Neutrino is. When you do full precision optimization, that means that you're compatible with basically any of the hardware. We wanted that by design because the universe of AI hardware out there is getting very heterogeneous. So we wanted to have a way of addressing that, which can plug into third-party software stacks. But when you combine this design space exploration with the low bit precision quantization, plus this compiler for these target hardware, we now are addressing like the ultra low power side of things. So not just Cortex-A CPUs, but going to Cortex-M as well, where you have super constrained, like 256 kilobytes of on-chip memory, or maybe 1 megabyte of on-chip memory. You just can't run a neural network on that stuff. You just can't. So we have to find more creative approaches to do this. And that's what's coming out is really more on that side. There's also just to mention on the software side of things and code. So I put a link to our GitHub at the end. Neutrino has a free version. We highly encourage researchers, academics to play around with it. Use it to compress models you're building, open source models. That's already there, and you can start playing around with that right away. The low-bit stuff is coming out in a community version later this year, where you can also apply this runtime side to your CPUs with like a Raspberry Pi or something to prototype it and play around with that as well. A couple examples before we wrap up here about where we're seeing the new opportunities created. I mentioned security, smart doorbells a lot. One of the things we've done in the computer vision space is actually apply the low bit precision stuff to do this whole one processor runs one thing, one processor runs another thing. A lot of devices are now being built with CPU, GPU, NPU, or CPU, FPGA, NPU. And so you want to leverage all these hardware in a way that's most efficient to get the most out of them, to give the best experience to a consumer. And the first trigger here is like, motion sensor is a very common sensor nowadays. It's incredibly cheap and ubiquitous, but it has a huge pain in the ass when it comes to false positives. In the context of home security, this might be a raccoon running through your backyard. It might be your dog. It might be your neighbor snooping around. It might be a robber. So getting more intelligent detection than just motion has been a first ambition. But because motion shots are so cheap, we need a cheap way of doing this. And that's where this first trigger comes from getting this quick little wake up. That's the bottom screen here, where right now you see low power, no person. We're just running this low, cheap little classifier constantly. Once that classifier wakes up, the second trigger, now we're saying, okay, what is it? It's saying, okay, we got a person here. Now it's in the high power mode. And then it's going to detect that person and use the accelerator to actually track that. So this were an actual threat scenario here, or someone's stealing the packages off your porch. This would be a far more intelligent way to actually have a product that addresses that, than just being able to say, hey, there was motion at the front door at 2 o'clock or something. That's the direction that this is taking here. And this preserves battery life dramatically, because if you're constantly running, as you can imagine, an NPU or constantly running a GPU, forget about battery life. It's not going to last. One very cool application, I'll wrap it up here, is one of my favorite ones, is some work we're doing in the automotive space. I don't know if anyone here has a Tesla. I know Elon Musk loves Texas too, but basically they've had this feature for a long time called Sentry Mode, where if someone's kind of looking in your windows of your car and stuff, Tesla will, while preserving its battery life, because it's a battery powered car, basically see if it's a threat or if it's just someone walking by. And if it is a threat, it's gonna have multiple levels of security to like either call the police, notify your phone, record the video. You can't record video constantly, right? So that's what this is really all about, is trying to use the cameras the car already has to get intelligent information around its surroundings, to perceive the environment while still being not annoying, so not too many false positives, but when there is a threat, actually getting it. And so what we've done is applied this work that I just mentioned, all of it, really, the compact model design, low bit precision quantization, using in this case, the CPU plus a GPU to detect basically what you're seeing here is people trying to break into a car. And when the detection on the left side goes from like yellow to red, these are different levels of threat detection. And the whole underpinning here is the car is off. This is a gas-powered vehicle. There are still those around. And even when the gas-powered vehicle is off, it needs to preserve its battery because it's off. And this is like 4 fisheye cameras running constant video. We have to find a way to do this efficiently while preserving the vehicle safety. And that's what we've done, with some of the work we've done here. So this is super cool. So to wrap it up, future directions, as I alluded to, combining this design space exploration plus quantization, that's been something we've been pursuing for some time, because that gets the best compression with the best accuracy retention. That's something that's of extreme value. There is continued innovation on the lightweight model design. There's constantly a new Pareto front of more accurate, more efficient detectors. The whole community is pursuing this heavily, and that's a fundamental facet of the space. The third one, alternative compiler and runtime options. So look at TVM, looking at RMNN, looking at a whole host of stuff from different hardware vendors. That's for commodity devices. We're talking about like the MCUs, the RISC-V, or RISC-V32. Big fan of RISC-V. That's something that we see more and more industry partners adopting. So we want to look at options to run AI on RISC-V. Fourth bullet point here. So I'm part of a technical program committee with TinyML that looks at on-device learning and also AutoML. AutoML is really a big one in terms of the tool chains and what people are using to build their AI. that's something that's, I think, starting to go from research to production. On-device learning is a really good field for pioneering. It's a combination of everything we talked about plus the training side. And that's where devices are going to start to just become incredibly powerful, because the data in the real world changes. The real world is constantly variable, and we want to be adapted to that. Devices have to learn in real time, depending on what it is. And the last one here, advanced R&D to implement ultra low bit operations in hardware. That's something where it kind of becomes obvious. Like if you have these low bit models, low bit precisions we want to do, it's going to be faster, more efficient if we can build it in hardware. That's a big bet, of course, in this space where algorithms are changing constantly. But we've seen the likes of Apple, the likes of Xilinx, for example, be doing this for some time. So that's a huge area of opportunity for both the computer science, electrical engineering sides of things. So that's all for me for today. Thank you very much for having me here. Thank you very much for everyone for attending. And I'm really looking forward to answering any questions.
Thank you, Davis. That's a great talk. I mean, it echoes with a lot of things we are doing in our own research lab as well. But there is a question from one of the students in the chat. Fatima, would you like to ask the question?
Sure. Thank you for the wonderful talk. I just had a question about quantization aware training. So in quantization aware training, does it start from an untrained model and then trains using low bit quantization? Or does it start from a network which has been trained on high precision and then it's tuned based on that?
It's the latter. So that's a great question. And to make it more precise, so we're talking about, say, for example, a detection task. We're starting from the full precision, so 32-bit trained model on that actual data set, and then introducing another training step where we have this quantization mode training. You can apply it to an untrained model with random weights, for example. You could apply it to a model that's already quantized to int8, but that's where we've seen more need for more improvements to get accuracy. The best practice has been taking this full precision model as trained, introducing this one quantization mode training step with these full precision weights and activations, and then out the other end comes this low precision model that's accurate. That's the best practice we've seen. If we are interested in looking at ways to quantize further, like an int8 model and quantizing it further, but that's something that needs more work.
Thank you.
I have another question from Vedant.
Hi there. Thanks for the great talk. So I had a question. So during optimization or quantization, how do you decide what is the compromisable range for the accuracy? So there will be a degradation in the accuracy for sure, right? When you are optimizing the model, adding the different layers in between, replacing the layer with the deep convolution here. So there is a degradation in the performance, right? How does the algorithm decide what is the compromisable range for the accuracy?
Yes, that's a great question. I wish I could do a show and tell here, but if you're curious to see how this actually looks, what I'm about to describe, you can check out Neutrino, the actual code base for it. There's a few demo videos online here, but the way it works is, the way we've addressed it is actually to have a user decide that we call it the delta. So there's going to be some degradation. Sometimes we to take a step back, the delta comes from the training data set. So what we have is we have this model and then a training data split with training, test, validation splits, for example. So we measure this delta I referred to, this accuracy degradation on those data splits, and we allow a user to define a explicit value, like maybe they have a delta of 1% or 5%. And the way we approach the problem is to find the maximum compression within that accuracy constraint, if that makes sense. So if they specify a 1% accuracy drop and we do one search iteration and we find a super compressed model like 30x, but the accuracy is a 5% drop, we then use that to seed another search stage to say, okay, let's get the accuracy back up. And then basically iterates through that in two phases. One's called exploration, one's called more boiling or annealing, where we start to do a more fine-grained search space. Like say we're getting close to that accuracy delta, like 1%, we start to do a very fine-grained search that only consumes a tiny bit. But the bottom line is that this is a user-defined criteria, because otherwise it's kind of like this open-ended problem of, well, let's just find the best accuracy possible. So we've approached this like a constraint. A user imposes linear constraint on accuracy, and then we try and find the best compression or best quantization scheme within that accuracy constraint. And in the software code, in the command line, when this is run, the user specifies a delta, and that delta is measured by their eval function on their data splits with their pre-trained model.
Oh, okay. Thanks.
Ms. Hamid, you said you had a few questions.
Yeah.
Too?
Yeah. Yeah, thank you for that. Very interesting. And I have 2 or 3 questions. One is the runtime you show for 1-bit and 2-bit weights is for the devices is ARM which supported 1-bit or 2-bit, or you just estimated this runtime?
Right.
Because
Yeah. So these devices do not support 1-bit or 2-bit operations. We're leveraging some of the existing vectorization or bit serial operations we can use for these convolutions at that low precision using the existing hardware intrinsics. Where there's no hardware that actually supports this actual 1-bit or 2-bit. You can think of it as a couple different ways, like packing 16 or 32 weights into a full precision operation, or more intricate stuff than that. So that's how it's we're not using like a real 1-bit or 2-bit at this stage, but there is some hardware that can do that. And that's what I was kind of alluding to in some of the slides, was that's where we actually do implement the real low precision operation in hardware. And that's where it's much, much faster.
And another question is it time to market for the DeepLite compiler or DeepLite software is important for you guys? Because, for example, if it takes like 1 week to do this quantization about training, that might be a problem for the customer. So what do you think?
Yeah, that's a really good question. So that's why I think the one-step quantization for training is much more in terms of time to market, to your question, attractive than these heavy-duty design space explorations. Sometimes the customer will say, I don't care how long it takes. I need to find the best model possible. But more often than not, it's not just the time to market, it's the cost of the compute time. Like if you're going to spin up an 8x, DGX server to do the search space and has 5 iterations, that's a cost too. And the people want that compute. So that's why we've tried to bring the neutrino side of things, the design space exploration side of things, to like one-shot architecture search, for example. And that's where the quantization for training becomes much more attractive. The way it will look when we talk to like in industry is it's a certain multiple of your current training time. So if they say my current training time is 24 hours, my current training time is 1 week, it's going to be another 24 hours or another 1 week. Usually they're okay with that, but of course, the faster the better is always the case.
And another question is, do you want this DeepLite software to be more generalized with different models? For example, finding a best optimal like precision for 10 models, or just go to the specific 1 models?
Yeah, there's a couple. So one of the things I didn't mention in this talk was we have 2 options for the software. One can be a single GPU. Actually, there's 3. One is for single GPU. One would be for one machine with multiple GPUs, and the other is for multiple machines with multiple GPUs. And the current way we do this is the latter you described, where we're trying to converge on a single model. So it's more the parallel in that sense. But because of this multi-GPU and multi-machine option, you can actually, it's quite difficult in terms of managing the training information, weights, and statistics of the training. But we actually want to explore multiple models in parallel and present multiple options back to someone with multiple trade-offs. That's that's kind of the idea with that. Hard to do when you have less compute, but when you have more, you can actually start to explore multiple design spaces actually, and then iterate around, like you said, like maybe not 10, that's quite intensive at this point, but multiple is the objective. Yeah.
Thank you.
That's a great question.
Yeah, Hamid is actually working on this, so you can see the pointed questions.
Makes sense, yeah.
I have a question for you, Davis. Like when you mentioned that you have reduced the bit size to 2 bits or 1 bit, you've shown this plots like on your VWW data set. It's a synthetic data set, right, from yours. And you have shown, if I recollect, that there is a degradation in performance, and maybe there is like 20% degradation. I do not recall the accurate numbers. But in general, when you are downscaling your bit size to that level, I would assume that there would be quite a bit of chance for randomness in your accuracy rather than like, just a drop by a certain percentage. So yes, it could be a chance at that point. So are you doing anything beyond just quantization at that point to ensure that the accuracy is dropping in a certain realm, or yeah, maybe if you can
Right.
shed some light there.
Yeah, I think I understand the question. And this is to the earlier question about how accuracy is measured, deciding accuracy. That's where I forgot to bring this up. But one of the things we've seen experimentally, consistently, both for the optimization and quantization, because of this randomness you just mentioned, is although we might observe some small degradation or manageable degradation on a training and test data split, consistently what we've seen is actually, and there are some techniques here that have helped with this in regularization, is on unseen data, 2-bit models can actually be even more robust than an int8 or a 32-bit model because they can often overfit, as you'd expect, to some data sets. When we introduce this extra step of optimization, quantization, it acts as like this regularizer on the model design. So we deploy it to unseen data. We can actually even have better false positives or better accuracy rates or better detection metrics than just quantizing in one step, for example. And there's a lot of work to be done here to, I think, make any firm judgments. But what we've seen, and this has been kind of crucial to us getting customers and investors, is that they can be more accurate on unseen data than the initial models. A lot of stuff to say there, but yeah, there is room for that, and we've observed that experimentally.
Right, and the performance of it being better on unseen data, I think there needs to be a lot more exploration there, right? And
Yes.
it depends on what it is trained on and a lot of other factors, right? Yeah, that's interesting.
Absolutely. I mean, one of our fears was that we'd converge on like a very locally optimized model and then put it in the wild, and it just, the accuracy goes to like 0 or something like this. But you know, with the right, I think it really comes down to the data curation techniques and consistently what we find from working with partners who have maybe big data sets or less curated data sets. That's really the lifeblood of this whole operation, is if it's well represented there, we have a better chance of getting a more performant model than if not.
Thank you so much, Davis, particularly showing our students and our researchers and Matrix the applications where you are like using these type of models and how DeepLite is contributing to building this energy efficient models that we deeply care about. So thank you so much for your time.
Thank you. Thank you, everyone. And thank you for having me.
Yeah. Bye.
Bye-bye.